Okay, the probability that she's a feminist bank teller, conditional on the signal that she's a liberal, under base rate neglect, is equal to 0.5, that false base rate again, times the probability that we would get the signal liberal if she was a liberal bank teller, divided by that same thing, plus same false base rate times the probability that she would be a liberal if she was not. I keep doing LBT. That's supposed to be an feminist bank teller. Feminist bank teller, not a feminist bank teller. Right. Which is equal to 0.75. That's how likely she is to be a liberal if she's a feminist bank teller. Times 0.75 plus 0.5, which is equal to 0.6. Okay? Because again, over and over again, the base rates are canceling out. And so we get exactly, sorry, I was about to say we get exactly the result that we see in the actual paper, in the actual study, which is that we, people who exhibit base rate neglect, would, under the condition that more feminist bank tellers are liberal than regular bank tellers, conclude that Linda is more likely to be a feminist bank teller than that she is to be a bank teller. Yeah. So Pallas's point is that this seems like a pointless exercise because, in fact, we don't believe that anybody really thinks that all these states of the world are equally likely. So this just feels like hand-waving. And I mean, you're kind of reiterating a point I made a few minutes ago, which is that this model, so it's a little bit less than perfectly satisfying for two reasons which are related. One is because the actual mathematical tweak, which is to set base rates equal, does not in itself capture any psychological realism. But it does insert psychological realism into the model because it has the mathematical result that the base rates disappear from the formula and are therefore neglected. So, I mean, I could just as easily have said the model is don't include the base rates. It actually doesn't matter whether we say the model is you set base rates equal or the model is you just leave the base rates out of the formula. It's the same thing. So I guess it's not as unsatisfying as I thought. Yeah, we're trying to maintain the structure of Bayes' rule when that just fundamentally isn't how things are done at all. People don't divide anything by anything. So I guess I have two things to say about that. One is, I think that your criticism is ultimately valid. I think, as I sort of said, I think this is an area of behavioral economics in which mathematical modeling has been less successful to date. And that may very well be because, I mean, when you think about intertemporal discounting, it sort of does seem intuitively right that people deflate, that if we were to model decision-making as people put a number on different outcomes and pick the biggest number, that they would deflate numbers that are way out in the future. It feels intuitively right that this idea of summing up utilities over different periods and then making the ones that are far away smaller, it kind of captures something, so let's keep that structure. And so it's not actually obvious that Bayes' rule even remotely begins to capture, even intuitively, any part of how people make these kinds of judgments. And I don't know, I'm a little bit out of my depth here as to why we're engaged in this exercise at all as a field. I know why I'm engaged as a professor. It's because I'm teaching the field. Why the field is engaged in this exercise, I don't yet know exactly sort of historically how we got here or why we're still here. But I'll say two things about it. One of which is there doesn't seem to be a better starting point, making itself obvious, and which is, again, sort of shouldn't be a very satisfying answer, isn't a very satisfying answer, but it's sort of where we've gotten to. And the other is there's just, as Matt Radin would say, lots and lots of situations in which it really should be how we make decisions. And those situations aren't, when we're deciding whether or not to get out of the way of a stick. But in the modern world, there's all kinds of situations where, if you're writing down a mathematical model of what any kind of normatively valid notion of what a sane person should do or what a rationally self-interested person should do, the answer is Bayes' rule. If you're trying to determine what mutual fund to invest in and all you have is signals of recent past success, you should be using Bayes' rule, or you're going to make mistakes that cost you money. And unless you claim you don't care about money, we have you red-handed, right? So we're going to want to write down models in which we do use Bayes' rule, and then we're going to want to be able to capture in those models parsimoniously the specific way in which you fail to implement Bayes' rule. So that's maybe a little bit more satisfying reason to stick with it, but it's not clear that it actually is an approach that winds up working. And I think what's true is that this line of behavioral economic modeling is a bit of a dead end at the moment. But I think it actually elucidates the project of behavioral economics pretty usefully. Okay, so thank you for the question. I apologize for the long-winded digression. The point I want to make about this isn't, aha, we figured out non-Bayesian probability inference. The point I want to make about this, satisfying or not satisfying, is that we started out with what seemed like two very different anomalies, right? People get the answer about the HID test wrong, and then they do this weird thing with Linda. And psychologists do not identify these as the same anomaly, right? This thing that we do with Linda is called representativeness, the representativeness heuristic. And the thing that we do with the HID test, psychologists for a long time have been calling the base rate fallacy. And when we start applying math to the thing, we get some insight into the possibility that, hey, maybe these things turn out to be the same thing. Now, again, this is an area where we haven't nailed down the right answer or even an answer that's particularly satisfying. It's just to give you an example of the way that bringing the rigor of mathematical modeling into psychology or applying it to psychological results can potentially render some insight. And psychologists are notorious, at least among economists, psychologists are notorious for over and over again discovering the same phenomenon, giving it a different name, and publishing a new paper. Right? And then if you write down a mathematical model of the phenomenon they claim to have discovered, you can say, look, these 5 things that you discovered over the last 60 years, they really are the same thing. And there are psychologists who recognize that. Not, Kahneman and Tversky being the most salient example. Let me give you another example of that. Or let me get started on showing you another example of that. And I think that this is actually a much better example. And I think this is a place where psychological realism has been more relevantly captured. So that's all for... Did it just go out? I don't have anything to flip it on with. If you're joining us on the internet, what's happening is I'm fiddling with the cord of the microphone so they can hang it around my neck. Okay. We're back in action. Ta-da! Hooray! All right. So lots and lots of situations, lost my stylus, in which a decision maker, before making a decision, gets to observe a sequence of signals, a sequence of related outcomes, related meaning signals that are generated by the same data generating process if you've taken econometrics or probability, but basically the same sort of underlying probabilistic machinery is generating a set of predictable but not perfectly predictable signals, or a set of random but not completely random signals. So, for example, a coach can observe the recent performance of a basketball player before deciding to put him in the game. A patient or doctor might observe the outcome of prior surgeries before deciding whether or not to undertake the surgery. And the one that we're going to focus on most is an investor might observe the short-term and long-term past performance of mutual funds before deciding which one to invest in. So I showed you an example where they just get one signal, the most recent quarter, but you could have multiple quarters, and you would have more signals. And then the question is, how well do people use those signals and aggregate them together to come up with the most accurate inference possible about the true state of the world? Okay, here are two pieces of evidence on how people form beliefs based on random sequences of signals. Now, when I say random sequences, I'm talking about not random meaning that there's some known probability that the signal will be generated, and that known probability is correlated with something that matters, but there's a random component, right? So if you're a high ability mutual fund manager, we're not saying that your performance is actually completely random. You're more likely to do a good job than a low ability, but there's still a random component around your mean. Okay? So the gambler's fallacy is a very well documented phenomenon in which people incorrectly believe that streaks won't continue. Okay? That coin's come up heads 5 times in a row. It can't possibly come up heads again. And the hot hand fallacy, which says that streaks will continue, right? I'm on a roll. I've rolled, and it wouldn't be the case with coins, but it would be something where you can't see the underlying distribution. And usually the canonical example is in sports. Oh, this guy's hit all his shots in a row. He must be on a hot streak, and it's bound to continue. So at first sight, these things look like they are exactly contradictory. But when we model them mathematically, we'll discover that the same model can explain both of them, and that the model actually captures some kind of relevant underlying psychological insight. All right. So gambler's fallacy, false belief that in a sequence of independent draws from a distribution, the outcome that hasn't occurred for a while is more likely to come up on the next draw. So for example, if a coin has come up heads 4 times in a row, tails is quote-unquote due. This paper never got published as a paper. It has recently come out in a book. That's not that helpful, so it's not on BSpace, but you can get most but not all of it if you search Google Books, where you will find most of the paper but without a few pages here and there. And here's what these guys did experimentally. They took a bunch of subjects and they randomly assigned them to 2 groups, a red group and a black group. There was nothing meaningful about these groups except that they got color assigned to them. And then each group was told, and this is a psychological experiment, so they used deception. You're not allowed to use deception in an economic experiment. Everybody was told that somewhere off in the background, a coin was going to be flipped 25 times, right? And then the sequence revealed. Or more importantly, that it was going to be flipped 22 times, and then on the third flip, people were going to make a choice based on what they thought the next flip was going to be. In reality, what they did was that they actually wrote down a predetermined sequence in which the first 17 flips were a mix of who knows what, and then there was a black one, and then 4 red in a row. So they set it up so that there'd be a streak of red. And then on the so-called 23rd flip, which I don't know for certain, but I'm guessing in reality it was the first flip because the first 22 were bogus, each participant was given a choice between either getting 70 points for sure. This is the kind of experiment where you earn points and then they're redeemed for cash at the end. And I think usually a point is a penny. I'm not quite sure. So you chose between 70 points for sure or a chance to win 100 points if the next flip was your color. Right? Now, we know that that's a 50-50 bet, right, for everyone in the group. And what we know is that if you take 70 points, if you take a chance to win 100 points on a 50-50 bet, which has an expected value of 50, over 70 points for sure, what does that tell us about your risk preferences? You are risk-seeking in a pretty big way, right? And that might be the case, but yeah. So they were told the experiment to coin actually has probability. I think what they were told was that it was an actual coin, but I don't know. I haven't read the paper. They did tell them that. They did tell them that it was a mix, and there was the left side, 4 red and 1 black. You can make it into the maximum likely estimate of the rate of being red is. That's correct. So the point made is that if you're not told that it's a fair coin, a 50-50 coin, and you're not told what the first 17 were, that if the only information you have about the coin is that it just came up 4 times in a row after 1 black, that if you had to make an estimate based on that small sample, you'd say, oh, that must be a biased coin with an 80% chance of coming up red. And we will see that type of error being made in situations where people don't know the baseline probability in a few slides. I'm going to go out on a limb and say they knew, because if they didn't know, it really would not be an interesting paper at all. And I was about to say it wouldn't have gotten published, and then I stopped because it didn't get published, but I doubt that's the reason why. Okay. So you might choose either way depending on your risk preferences, which is why the experiment is set up the way it is, because what they're interested in is not people's choices, but how their choices vary depending upon which color they were randomly assigned. And it turns out that 5 out of 29 red subjects chose to take the gamble, and 22 out of 30 black subjects chose to take the gamble. And what that suggests is that they all seem to think, or at least some significant subset of these people, seem to think that black is more likely to come up than red. Right? It's fine if they all want the gamble because they're all risk-loving. It's not okay that they differ depending on which side of the bet they're given, right? The red side or the black side of the bet. So this is a pretty strong indication that that people had a wrong belief about the probability of the next flip. Okay? The next piece I think is clever and sort of strengthens the appeal of the result in some way. They then did a variation where the 23rd coin flip was delayed by 24 minutes. I don't know why 24. So they showed them the sequence, and they said, okay, now we're going to take a break and go and do something else. I don't know what. And then they come back, and they're required to review the first 22 flips. So they see the sequence, the streak of reds again. And this time, these numbers are statistically indistinguishable from one another. Okay? It still looks like a lot of people are going for that risky bet, and a little bit more of the black than red are going for it. So it suggests that there might still be a bit of a belief in the gambler's fallacy, although a much weaker one. And I don't know, but I'm guessing that difference is probably statistically insignificant. But what they seem to think is that giving the coin a rest makes it more likely that the streak will continue. Right? So let me just say something about that result and the way it's reported in the paper. The paper is not about Bayes' rule at all. The paper is about a hypothesis that people make errors in probabilistic judgments because of anthropomorphization of physical objects, that they treat the coin as if it had human attributes, right? So I'm red. The coin's trying really hard to make me happy by coming up red, and then it gets tired, so if I let it rest, it'll go back to being a good coin again, or a normal coin, or something like that. And so they're basically testing a theory of some kind of animistic anthropomorphization of objects, okay? And they cite other examples that they think that this might be an explanation for. And I don't claim that that's not true. I think human beings are guilty of anthropomorphizing lots and lots of silly things, not least of which are their pets, and sometimes to the detriment of the pet. But for the purposes of coming up with some kind of generalization that we can use in understanding important economic decisions, it just turns out to be not a particularly robust hypothesis, not particularly generalizable, not something that we can really apply the economist's way of thinking to. Right? Because the economist's way of thinking is to put something into mathematical terms and then see if we can just crank it up and use it to draw inferences about other things. So we'll come back to that in a bit. Let's look at this seemingly contradictory piece of evidence about how people make judgments, the hot hand fallacy. Basketball fans, players, and coaches, and lots of other people, anecdotally believe that there is systematic variation in a player's performance from day to day. Now, there may very well be systematic variation in a player's performance. Now, sorry, let me back up and be clear what I mean by that. I don't mean that whether or not a player hits their shots on any given day varies, but that the underlying probability that they will hit their shots varies, right? So that from day to day, whether or not you hit a shot is a partially random, it's a stochastic process. It's your ability plus an error term, okay? And so what fans and coaches and players and lots of other people believe is that that underlying probability that somebody will make, their player will make their shots on a given day varies systematically from day to day in a big way, okay? Now that may not be, it may be correct. So it may not be a fallacy to think that the likelihood that a particular player is going to make any given shot on any given day varies from day to day. The fallacy is to think that the variation is much bigger than it actually is, okay? So what that suggests about people's beliefs about sequences of random, or I want to not say random, stochastic outcomes that have a random component, is that a player is more likely to make his or her next shot if they've made recent shots, right? Which seems to be exactly the opposite of the gambler's fallacy. And that would seem to suggest that a player's successful shots cluster together more than their baseline probability of success would imply. Okay? So you look at somebody's baseline ability over a lot of games, and then predict, sort of just generate random sequences of shots based on their underlying success probability, their underlying ability, and you'll get clustering, right? You will see that their actual success rate varies over time, and there'll be clusters where they're doing well and clusters where they're not. The hot hand fallacy basically is saying that people think that their performance will cluster more than it actually does. Okay? All right, so that's the hot hand fallacy. Now there's this lovely test of it. Gilovich, Volone, and Tversky interviewed players and coaches to find out whether or not they believe that there's this variation, and overwhelmingly they do. And then what we want to do is to find out whether or not they're right. Right? Sorry, this is incorrect. They interviewed them not to find out if they believe in the hot hand fallacy, but whether they believe in the hot hand phenomenon. Right? And then we're going to find out whether it's a fallacy. So then what they did was they got a bunch of data on the Philadelphia 76ers from the 1980-81 season, which was a season during which the Philadelphia 76ers had a player on their team named Andrew Toney, who was the most notorious streak shooter of the day. He was hot some days and not on others. So it just was clear that there was something going on with his performance from one day to the next. His underlying probability of getting the